Okay, everybody. Last video for Chapter 5, and actually two pretty easy concepts: noble gas core configuration and electron dot diagrams. So I'm going to start with the noble gas core configurations. We said that there were two types of electrons: core electrons and valence electrons. And in a configuration, for instance, if you have something like, let's do oxygen. All right, oxygen has 8 electrons. And if we work it out, we get 1s2, 2s2, 2p4. And if you look at what's stable in the oxygen atom, 2 of the electrons are what we call core electrons, and the other 6 are what we call valence, which are available for bonding. So when you complete an energy level, these electrons become stable. So notice in the oxygen there were 2 core electrons and 6 valence electrons. That means that's the same number of electrons as if you had a completed first energy level. You filled all the space in the first energy level. Now if you take a look at sulfur, which has 16 electrons, again, we get a configuration of 1s2, 2s2, 2p6, 3s2, 3p4. And it turns out that there are 10 core electrons, and there are a total of 6 valence electrons, just like in oxygen, 6 valence electrons. And with the 10 electrons, what you've done is you've completed the first energy level and the second energy level. We're going to write first energy level, second energy level filled with electrons. When you have a full energy level, that renders those electrons stable. So I'm going to write that down. Full energy level is stable. Okay, so if we go back and write the element that has 2 electrons, we would say that this has a helium core. It has a helium core, and then 2s2, 2p4, 6 valence electrons outside of it. So here's my core, and then the 2s2, 2p4, that's my valence shell. Here, we said that there are 10 core electrons, so the first and second energy levels are filled. And we could rewrite this, the element with 10 electrons, as neon. So we rewrite this as a neon core, and then 3s2, 3p4. Well, what have you learned about in the past about the noble gases? Well, if you go to the noble gases, we said that when we were signing oxidation numbers, we assigned group 18 a value of 0. 17 -1, 16 -2, and what we said was generally these elements in group 18 are fairly unreactive. Now they used to think that they were completely unreacted, and they called them the inert gases, inert meaning unreactive, but we've since found that we can make them react with other things. Again, big human brains, we can control the environment. So a better way of writing the oxygen configuration is to write helium core 2s2, 2p4. That way we know there are 6 electrons available for bonding, and then the ones in the core have the same arrangement as helium, which is stable. For sulfur, a better way of writing the configuration would be to write a neon core, 3s2, 3p4, and that those 10 electrons are stable because they're in the same arrangement as neon. Okay, so how do you do that using the periodic table? Glad you asked. We want to be able to do this quickly. Now, one way you can write the core is to go through and write out the whole configuration and then find your full energy levels. But you know, I like to use the periodic table, but we'll do it the long way first. All right, suppose we have selenium. All right, right there on the periodic table. Element number 34, so it's got 34 electrons when it's neutral. So we're going to write selenium. 34 electrons. And if we follow along on the periodic table, or if we do an energy diagram, the configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4. Okay. So when we write the noble gas configuration, one of the things we can do is take a look at the energy level that's not full. The fourth energy level is not full. So everything from here on, that's going to be a valence electron. And everything before that, those are my core electrons. So you look for the highest energy number that is not full, and then you break up your pattern that way and say, all right, core electrons, how many electrons are there? 2, 4, 10, 12, 18 electrons. Which noble gas has 18 electrons? Argon. Argon has 18 electrons. So what we're going to do is we're going to write argon core, and then we just transfer these valence electrons down. 4s2, 3d10, 4p4. And that is certainly one way of doing it, but it's a longer way. Here's a shorter way. Go to your periodic table. Find selenium. Now, let's work our way back down to the next lower noble gas. It has to be lower. You can't go higher because you don't have those electrons, but we can go lower. So this is going to be an argon core. Now, after the argon core, what are you moving through to get back to selenium? Well, you're moving through the 4s. You're moving through the 3d. And then you have 4p1, 4p2, 4p3, 4p4 to get back to selenium. So it's an argon core, 4s2, 3d10, 4p4. And that's how I do it. Last part of the chapter, since you're going to practice this in the book and in recitation, is something called an electron dot diagram. And later we're going to use these to create Lewis dot diagrams, which are electron diagrams involving compounds. But right now we're just doing atoms. Electron dot diagrams refers to neutral atoms. Okay. Here's the format. X stands for the element that you're dealing with. Your S electrons, valence electrons that is, your valence electrons go around the element X. So you put your S electrons there, your PX to the east, PY to the south, and PZ to the west, and you fill them in accordance to Hund's rule. So if you have valence electrons, they spread out PX, PY, PZ before going back to the PX. Now, there are other formats for writing this. You don't have to start with S in the north part. You could put it on the east part, but if you do that, then PX goes to the south, PY to the west, PZ to the north. Or if you start S in the south, then PX goes to the west, PY north, PZ east. Then, of course, the other option would be, let's start S to the west, then we go PX, PY, PZ, clockwise. All right, so suppose they give you, well, even before we do that, something to notice about these valence electrons. Notice that in the diagram, they're only using the S shell, right, and the P shell electrons. When we deal with S and P valence electrons, they are called primary valence. And they're used to create things like ionic and covalent bonds. These are strong bonds. The D shell electrons and the F shell to some extent too, they are something called secondary valence. Now these are weaker bonds, like when we had the copper sulfate pentahydrate. The pentahydrate part was connected using secondary valence, and these create weak, what's called coordination bonds. So in other words, if we're doing an electron dot diagram, there are no d electrons in an electron dot diagram, only the s and p, because we're just showing primary valence. All right, so let's see what a couple of these look like. Suppose we have hydrogen. Hydrogen has one electron. It's in a 1s1 configuration. So we write H for hydrogen, and then we put a dot to the north for its valence electron. Let's try another. Beryllium has 4 electrons, and they are 1s2, 2s2. Now, the 1s2 is in a noble gas core, so really core configurations are better for this exercise. Like if I put this in a helium core, then I have 2s2 outside of it, and the 2s2, those are my valence electrons. So those are the ones that go in the diagram, valence electrons. So I would write beryllium, and then I would put 2 dots. Let's try another one. All right, suppose I have nitrogen. Nitrogen has 7 electrons, and that is going to be a helium core, 2s2, 2p3 configuration. So I have these 5 valence electrons right here. I'm going to put them around the nitrogen, 2 for the s shell, 1 for the px, 1 with the py, 1 with the pz, according to Hund's rule, spreading them out. So there's the electron dot for nitrogen. And then the last example, scandium. And in scandium we said that that is an argon core, 4s2, 3d1. So scandium has an electron dot diagram that looks like that. Well, why? What happened to the 3rd electron? Do I sound convincing? What happened to the 3rd electron? I'm so surprised. All right, this is secondary valence. And secondary valence electrons are not included in an electron dot diagram. So the only dots that go in there are the 4s2 electrons. And folks, that's it. That's as easy as it gets. All right, so, but you got to practice. It's all relative knowledge. If you wait until the test day to be the first day that you practice, you probably won't do well. All right, good luck.